In this live, we will be doing reading of chapter number 7, Motion of Grade 9 Science. So let's start with the reading of chapter number 7. Whenever you will be hearing to the audio of this chapter, I would like to request to share it with your friends so that everybody can hear it. These audios are really helpful once you are done with the chapter and you have to do the revision. So basically, in classes 9 and 10th, NCRT is just like your Bible. So you should definitely go on reading line by line of each NCRT chapter. Just give me a second and then we'll start. So the student who has joined right now may share it with their friends. Let's start with the reading of the motion chapter, chapter number 7. In everyday's life, we see some objects at rest and others in motion. Birds fly, fish swim, blood flows through veins and arteries, and cars move. Atoms, molecules, planets, stars, and galaxies are all in motion. We often perceive an object to be in motion when its position changes with time. However, there are situations where the motion is inferred through indirect evidences. For example, we infer the motion of air by observing the movement of dust and the movement of leaves and the branches of trees. What causes the phenomenon of sunrise, sunset, and changing of seasons? It is due to the motion of the earth. If it is true, why don't we directly perceive the motion of the earth? An object may appear to be moving for one person and stationary for some other. For the passengers in a moving bus, the roadside trees appear to be moving backwards. A person standing on the roadside perceives the bus along with the passengers as moving. However, a passenger inside the bus sees his fellow passengers to be at rest. What do these observations indicate? So let's move further. Most motions are complex. Some objects may move in a straight line, others may take a circular path, some may rotate, and a few others may vibrate. There may be situations involving a combination of these. In this chapter, we shall first learn to describe the motion of objects along a straight line. We shall also learn to express such motions through simple equations and graphs. Later, we shall discuss ways of describing circular motion. So we are done with this. We are moving to the right side of this page, first page of the motion chapter from your NCRT. So activity 7.1, discuss whether the walls of your classroom are at rest or in motion. Activity 7.2, have you ever experienced that a train in which you are sitting appears to move while it is at rest? Discuss and share your experience. Think and act. We sometimes are endangered by the motion of objects around us, especially if that motion is erratic and uncontrolled, as observed in a flooded river, a hurricane, or a tsunami. On the other hand, controlled motion can be a service to human beings, such as in the generation of hydroelectric power. Do you feel the necessity to study the erratic motion of some objects and learn to control them? 7.1, describing motion. We describe the location of an object by specifying a reference point. Let us understand this by an example. Let us assume that a school in a village of 2 kilometers north of the railway station. We have specified the position of the school with respect to the railway station. In this example, the railway station is the reference point. We should have also chosen other reference points according to our convenience. Therefore, to describe the position of an object, we need to specify a reference point, which is known as the origin. So we are done with the reading of this page. We are moving to the next page, that is page number 73 of your NCRT. 7.1.1, motion along a straight line. The simplest type of motion is the motion along the straight line. We shall first learn to describe this by an example. Consider the motion of an object moving along a straight path. The object starts its journey from O, which is treated as its reference point, figure 7.1. Let A, B, and C represent the position of the object at different instants. At first, the object moves through C and B and reaches A. Then it moves back along the same path and reaches C through B. So figure 7.1 is giving you the positions of an object on a straight line path. Let's move to the next paragraph. The total path length covered by the object is OA plus AC, that is 60 kilometer plus 35 kilometer is equals to 95 kilometer. This is the distance covered by the object. To describe distance, we need to specify only the numerical value and not the direction of motion. There are certain quantities which are described by specifying only their numerical values. The numerical value of a physical quantity is its magnitude. From this example, can you find out the distance of the final position C of the object from the initial position O? This difference will give you the numerical value of the displacement of the object from O to C through A. The shortest object the shortest distance measured from the initial to the final position of an object is known as the displacement. Can the magnitude of the displacement be equal to the distance traveled by an object? Consider the example given in figure 7.1. For motion of the object from O to A, the distance covered is 60 km and the magnitude of displacement is also 60 km. During its motion from O to A and back to B, the distance covered is equals to 60 kilometer plus 25 kilometer is equals to 85 kilometer, while the magnitude of displacement is equals to 35 kilometer. Thus, the magnitude of displacement 35 kilometer is not equal to the path length, which is 85 kilometer. Further, we will notice that the magnitude of the displacement of a course of motion may be zero, but the corresponding distance covered is not zero. If we consider the object to travel back to O or 0, the final position coincides with the initial position and therefore the displacement is 0. However, the distance covered in the journey OA plus AO is equals to 60 plus 60, that is 120 kilometers. Thus, two different physical quantities, the distance and the displacement, are used to describe the overall motion of an object and to locate its final position with reference to its initial position at a given time. Activity 7.3. Take a meter scale and a long rope. Walk for one corner of a basketball court to its opposite corner along its sides. Next, measure the distance covered by U and magnitude of the displacement. What difference would you notice between the two in this case? Activity 7.4. Automobiles are fitted with a device that shows the distance traveled. Such a device is known as odometer. A car is driven from Bhubaneswar to New Delhi. The difference between the final reading and the initial reading of the odometer is 1850 kilometer. Find the magnitude of the displacement between Bhubaneswar and New Delhi by using the road map of India. So let's move on to the next page now. And here we are on page number 74 of your NCERT. So the in-text question, there are three. So question number one, an object has moved through a distance. Can it have zero displacement? If yes, support your answer with an example. Next, a farmer moves along the boundary of a square field of side 10 meter in 40 seconds. What would be the magnitude of displacement of the farmer at the end of 2 minutes 20 seconds from his initial position? Question number 3, which of the following is true for the displacement? A, it can't be 0. B, its magnitude is greater than the distance traveled by the object. So we are coming to the next heading 7.1.2, uniform motion and non-uniform motion. Consider an object moving along a straight line. Let it travel 5 meter in the first second, 5 meter more in the next second, 5 meter in the third second and 5 meter in the fourth second. In this case, the object covers 5 meter in each second. As the object covers equal distances in equal intervals of time, it is said to be in uniform motion. The time interval in this motion should be small. In our day-to-day life, we come across motions where objects cover unequal distances in equal intervals of time. For example, when a car is moving on a crowded street or a person is jogging in a park, there are some instances of non-uniform motion. Activity 7.5. The data regarding the motion of two different objects A and B are given in table 7.1. Examine them carefully and start whether the motion of the object is uniform or non-uniform. So here the table has been given to you, table 7.1. We are moving to the next topic, that is 7.2, measuring the rate of motion. So I have flipped the page and we are on page number 75 of the motion chapter, grade 9. Look at the situations given in figure 7.2. If the bowling speed is 143 km per hour in figure 7.2a, what does it mean? What do you understand from the signboard in figure 7.2b? Different objects may take different amounts of time to cover a given distance. Some of them move fast and some move slowly. The rate at which objects move can be different. Also, different objects can move at the same rate. One of the ways of measuring the rate of motion of an object is to find out the distance traveled by the object in unit time. The quantity is referred to as the speed. The SI unit of speed is meter per second. This is represented by the symbol meter per second or m/s. The two units of speed include centimeter per second, kilometer per hour. So the units are written in the bracket. To specify the speed of an object, we require only its magnitude. The speed of an object need not to be constant. In most cases, objects will be non-uniform motion. Therefore, we describe the rate of motion of such objects in terms of their average speed. The average speed of an object is obtained by dividing the total distance traveled by the total time taken. That is, average speed is equal to total distance traveled divided by total time taken. If an object travels a distance s in time t, then its speed is v, that is written as v is equals to s upon t. Let us understand this by an example. A car travels a distance of 100 km in 2 hours. Its average speed is 50 km per hour. The car might have traveled at 50 km per hour at all the time. Sometimes it might have traveled faster and sometimes slower than this. Example 7.1. An object travels 16 meter in 4 seconds and then another 16 meter in 2 seconds. What is the average speed of the object? Solution is total distance traveled by the object is 16 plus 16 is equals to 32 meter. Total time taken will be 4 seconds plus 2 seconds is equals to 6 seconds. Let's come to the right side of the same page. Average speed is equals to total distance traveled is divided by total time taken. So it will be 32 divided by 6 seconds. It will become 5.33 meter per second. Therefore, the average speed of the object is 5.33 meter per second. 7.2.1 speed with direction. The rate of motion of an object can be more comprehensive if we specify its direction of motion along with its speed. The quantity that specifies both these aspects is called velocity. Velocity is the speed of an object moving in a definite direction. The velocity of an object can be uniform or variable. It can't be changed by changing the object's speed, direction of motion, or both. When an object is moving along the straight line at a variable speed, we can express the magnitude of its rate of motion in terms of average velocity. It is calculated in the same way as we calculate average speed. In case the velocity of the object is changing at its uniform rate, then average velocity is given by the arithmetic mean of initial velocity and final velocity for a given period of time. That is, average velocity is equals to initial velocity plus final velocity divided by 2. Mathematically, it would be V average is equals to U plus V by 2, where V average is the average of velocity, U is the initial velocity, and V is the final velocity of the object. Speed and velocity have the same units, that is meter per second. Activity 7.6. Measure the time it takes you to walk from your house to your bus stop or to your school. If you consider that your average walking speed is 4 km per hour, estimate the distance of the bus stop or school from your house. Next page, page number 76 of the chapter Motion, class 9th. Activity 7.7. At a time when it is cloudy, there may be frequent thunder and lightning. The sound of thunder takes some time to reach you after you see the lightning. Can you answer why this happens? Measure this time interval using a digital wristwatch or a stopwatch. Calculate the distance of the nearest point of lightning. Speed of sound in air is equals to 346 meter per second. Questions 1. Distinguish between speed and velocity. 2. Under what conditions is the magnitude of average velocity of an object equal to its average speed? 3. What does the odometer of an automobile measure? 4. What does the path of an object look like when it is in uniform motion? 5. During an experiment, a signal from the spaceship reached the ground station in 5 minutes. What was the distance of the spaceship from the ground station? The signal travels at the speed of light, that is 3 into 10 to the power 8 meter per second. Example 7.2. The odometer of a car reads 2000 km at the start of a trip and 2400 km at the end of the trip. If the trip took 8 hours, calculate the average speed of the car in kilometer per hour and meter per second. Solution: distance covered by the car S is equals to 2400 kilometer minus 2000 kilometer, that will give you 400 kilometers. Time elapsed is 8 hours. So average speed will be calculated as V average is equals to S by T, 400 by 8, that will give you 50 kilometer per hour. We are on the right side of the same page. So 50 kilometer per hour is equals to 1000 divided by 1 into 1 by 3600 will give you, on calculating, 13.9 meter per second. The average speed of the car is 50 kilometer per hour or 13.9 meter per second. Example 7.3. Usha swims in a 90-meter long pool. She covers 180 meter in 1 minute by swimming from one end to the other and back along the same straight path. Find the average speed and the average velocity of Usha. So total distance covered by Usha is 1 minute. In 1 minute is 180 meter. Displacement of Usha in 1 minute is 0 meter. Average speed is equals to total distance covered divided by total time taken. So it will be 180 divided by 1 is equals to 180 by 1 into 1 by 60, that will give you 3 meter per second. Average velocity will be displacement upon total time taken is equals to 0 divided by 60 meter per second. So the average speed of Usha is 3 meter per second and our average velocity is 0 meter per second. 7.3. Rate of change of velocity. During uniform motion of an object along a straight line, the velocity remains constant with time. In this case, the change in velocity of the object of any time interval at any time interval is zero. However, in non-uniform motion, velocity varies with time. It has different values of different instants and at different points of the path. Thus, the change in velocity of the object during any time interval is not zero. Can we now express the change in velocity of any object? Let's move to page number 77. I hope it is visible. Let's change the angle a bit. So it is to answer such a question, we have to introduce another physical quantity called acceleration, which is a measure of the change in the velocity of an object per unit time. That is, acceleration is equals to change in velocity divided by time taken. So if the velocity of an object changes from an initial value u to the final value v in time t, the acceleration a is equals to v minus u by t. This kind of motion is known as accelerated motion. The acceleration is taken to be positive if it is in the direction of velocity and negative when it is opposite to the direction of velocity. The SI unit of acceleration is meter per second square. If an object travels in a straight line and its velocity increases or decreases by equal amounts in equal intervals of time, then the acceleration of the object is said to be uniform. The motion of a freely falling body is an example of uniformly accelerated motion. On the other hand, an object can travel with non-uniform acceleration if its velocity changes at a non-uniform rate. For example, if a car traveling along a straight road increases its speed by unequal amounts in equal intervals of time, then the car is said to be moving with non-uniform acceleration. Activity 7.8. In your everyday life, you come across a range of motions in which A. Acceleration is in the direction of motion. B. Acceleration is against the direction of motion. C. Acceleration is uniform. D. Acceleration is non-uniform. Can you identify one example each of the above type of motion? Example 7.4. Starting from a stationary position, Rahul paddles his bicycle attain a velocity of 6 meter per second. Then he applies brakes such that the velocity of the bicycle comes down to 4 meter per second in the next 5 seconds. Calculate the acceleration of the bicycle in both the cases. Solution: in the first case, initial velocity is 0, final velocity is 6 meter per second, time is 30 seconds. From equation 8.3, we have A is equals to V minus U upon T. So substituting the given values of U, V and T in the above equation, we get A is equals to 6 minus 0 by 30. So it will give you 0.2 meter per second square. In the second case, initial velocity is 6, final is 4, t is 5. So acceleration will be calculated with the same formula as minus zero point 0.4 meter per second square. The acceleration of a bicycle in the first case is 0.2 meter per second square, and in the second it is minus 0.4 meter per second square. In text questions, one, what will you say a body is in one, uniform motion, second, non-uniform acceleration. It's uniform acceleration and non-uniform acceleration. Two, a bus decreases its speed from 80 kilometer per hour to 60 kilometer per hour in 5 seconds. Find the acceleration of the bus. Three, a train starting from a railway station and moving with uniform acceleration attains a speed of 40 kilometer per hour in 10 minutes. Find its acceleration. 7.4. So we are on page number 78 of the motion chapter. 7.4, graphical representation of motion. Graphs provide a convenient method to present basic information about a variety of events. For example, in the telecast of one-day cricket match, vertical bar graphs show the run rate of the team in each over. As you have studied in mathematics, a straight line graph helps in solving a linear equation having two variables. To describe the motion of an object, we can use line graphs. In this case, line graphs show dependence of one physical quantity such as the distance or velocity on another quantity such as time. 7.4.1, distance time graphs. The change in the position of an object with time can be represented on the distance time graph, adopting a convenient scale of choice. In this graph, time is taken along the x-axis and the distance is taken along the y-axis. Distance time graphs can be employed under various conditions where objects move with uniform speed, non-uniform speed remains at rest, etc. So figure 7.3 is showing you the distance time graph of an object moving with uniform speed. We know that when an object travels equal distances in equal intervals of time, it moves with uniform speed. It shows that the distance traveled by the object is directly proportional to time taken. Thus, for uniform speed, a graph of distance traveled against time is a straight line as shown in figure 7.3. The portion OB of the graph shows that the distances increase at a uniform rate. Note that you can also use the term uniform velocity in place of uniform speed if you take the magnitude of displacement equal to the distance traveled by the object along the y-axis. We can use the distance time graph to determine the speed of an object. To do so, consider a small part of AB of the distance time graph shown in figure 7.3. Draw a line parallel to the x-axis from point A and another line parallel to y-axis from point B. These two lines meet each other at point C to form a triangle ABC. Now on the graph, AC denotes the time interval T2 minus T1, while BC corresponds to the distance S2 minus S1. We can see from the graph that as the object moves from the point A to B, it covers the distance S2 minus S1 in time T2 to T1. So the speed v of the object therefore can be represented as v is equals to s2 minus s1 divided by t2 minus t1. We can also plot the distance time graph for accelerated motion. Table 7.2 shows the distance traveled by a car in a time interval of 2 seconds. So this table 7.2 is showing you distance traveled by a car at regular time intervals. Now we are moving to page number 79. Here we go. Figure 7.4 distance time graph of a car moving with non-uniform speed. The distance time graph for the motion of the car is shown in figure 7.4. Note that the shape of this graph is different from the earlier distance time graph, figure 7.3, for uniform motion. The nature of this graph shows non-linear variation of the distance traveled by the car with time. Thus, the graph shown in figure 7.4 represents motion with non-uniform speed. 7.4.2 Velocity time graphs. The variation in velocity with time of an object moving in a straight line can be represented by a velocity time graph. In this graph, time is represented along the x-axis and the velocity is represented along the y-axis. If the object moves at uniform velocity, the height of its velocity time graph will not change with time, figure 7.5. It will be a straight line parallel to x-axis. Figure 7.5 shows the velocity time graph for a car moving with uniform velocity of 40 km per hour. We know that the product of velocity and time given displacement of an object moving with uniform velocity. The area enclosed by velocity time graph and the time axis will be equal to the magnitude of the displacement. To know the distance moved by the car between time t1 and t2 using figure 7.5, draw perpendiculars from the point corresponding to the time t1 and t2 on the graph. The velocity of 40 km per hour is represented by the height AC or BD, and the time t2 minus t1 is represented by the length AB. So the distance s moved by the car in time t2 minus t1 can be expressed as s is equals to AC CD 40 t2 minus t1, that will give you 40 t2 minus t1, area of the rectangle ABCD shaded in figure 7.5. We can also study about uniformly accelerated motion by plotting its velocity time graph. Consider a car being driven along a straight road for testing its engine. Suppose a person sitting next to the driver records its velocity after every 5 seconds by noting the reading of the speedometer of the car. The velocity of the car in kilometer per hour as well as in meter per second at different instant of time is shown in table 7.3. So table 7.3 is showing you the velocity of the car at regular intervals of time. So we are done with this page as well. We are moving to page number 80 and we are on its left side. In this case, the velocity time graph for the motion of the car is shown in figure 7.6. The nature of the graph shows that velocity changes by equal amounts in equal intervals of time. Thus, for all uniformly accelerated motion, the velocity time graph is a straight line. So figure 7.6 is showing you velocity time graph of a car moving with uniform acceleration. You can also determine the distance moved by the car from its velocity time graph. The area under the velocity time graph gives the distance, magnitude of displacement moved by the car in a given interval of time. If the car would have been moving with uniform velocity, the distance traveled by it would be represented by the area ABCD under the graph shown in figure 7.6. Since the magnitude of the velocity of the car is changing due to acceleration, the distance s traveled by the car will be given by the area ABCDE under the velocity time graph figure 7.6. That is, S is equals to area ABCDE, the area of rectangle ABCD plus area of triangle ADE. So it will be calculated as AB into BC plus half of AD into DE. In the case of non-uniformly accelerated motion, velocity time graphs can have any shape. So the shapes of the graph can be seen in figure 7.7, velocity time graphs of an object in non-uniformly accelerated motion. Figure 7.7a shows a velocity time graph that represents the motion of an object whose velocity is decreasing with time, while figure 7.7b shows the velocity time graph representing the non-uniform variation of velocity of the object with time. Try to interpret these graphs. Activity 7.9. The times of arrival and departure of a train at three stations A, B, and C, and the distance of stations B and C from station A are given in table 7.4. So 7.4 is showing you the distances of station B and C from A and the times of arrival and departure of the train. So plot and interpret the distance time graph for the train, assuming that its motion between any two stations is uniform. So ultimately, we have reached on page number 81 of this chapter, motion. Activity 7.10. Firoz and his sister Sanya go to school on their bicycles. Both of them start at the same time from their home but take different times to reach the school, although they follow the same route. Table 7.5 is showing you the distance traveled by them in different times. So you are required to plot the distance time graph for their motions on the same scale and interpret. Now, the in-text questions that you can see written in blue. Question number 1, what is the nature of the distance time graphs for uniform and non-uniform motion of an object? Question number 2, what can you say about the motion of an object whose distance time graph is a straight line parallel to the time axis? Question 3, what can you say about the motion of an object if its speed time graph is a straight line parallel to the time axis? Uh, Next one, this right side of the page. Question number 4, what is the quantity which is measured by the area occupied below the velocity time graph? 7.5. Equations of motion. When an object moves along a straight line with uniform acceleration, it is possible to relate its velocity, acceleration during motion, and the distance covered by it in a certain time interval by a set of equations known as the equations of motion. For example, for convenience, a set of three such equations are given below. V is equals to u plus at, s is equals to ut plus half at square, 2as is equals to v square minus u square, where u is the initial velocity of the object which moves with uniform acceleration, a for time t, v is the final velocity, and s is the distance traveled by the object in time t. Equation 7.5 describes the velocity time relation, and equation 7.6 represents the position time relation. Equation 7.7, which represents the relation between the position and the velocity, and can be obtained from equation 7.5 and 7.6 by eliminating t. These three equations can be derived by graphical method. Example 7.5, a train starting from rest attains a velocity of 72 km per hour in 5 minutes, assuming that the acceleration is uniform. Find 1, the acceleration, and 2, the distance traveled by the train for attaining this velocity. Solution, we have been given u as 0, v 72 km per hour is equals to 20 meter per second, and t 5 minutes is equals to 300 seconds. So one equation 7.5, we know that a is equals to v minus u upon t. So it will give you 20 minus 0 by 300 is equals to 1 by 15 meter per second square. So we are coming to the next page. So this is one page that is left, 2 and 3. We are just finishing in few minutes. Let's come on to this side, page number 82, left side of the motion chapter. So equation 2, from equation 7.7, we have 2 as v square minus u square is equals to v square minus 0. Thus, s is equals to v square upon 2a is equals to 20 divided by 2 into 1 by 15. That will give you 3000 meter or 3 kilometer. The acceleration of the train is 1 by 15 meter per second square, and the distance traveled is 3 kilometer. Example 7.6, a car accelerates uniformly from 8 km per hour to 36 km per hour in 5 seconds. Calculate 1, the acceleration, and 2, the distance covered by the car in that time. Solutions, we are given that u is equals to 18 km per hour or 5 meter per second, v is equals to 36 km per hour or 10 meter per second, and t is equals to 5 seconds. So from equation 1, from equation 7.5 part 1, we have a is equals to v minus u by t is equals to 10 minus 5 upon 5 will give you 1 meter per second square. Part 2 from equation 7.6, we have S is equals to ut plus half at square. So it will give you 37.5 meter for after calculating. The acceleration of the car is 1 meter per second square and the distance covered is 37.5 meter. Example 7.7, the brakes applied to a car produce an acceleration of 6 meter per second square in the opposite direction to the motion. If the car takes 2 seconds to stop after the application of the brakes, calculate the distance it travels during this time. Solution, we have been given A is equals to 6 meter per second, T 2 second, V 0 meter per second. From equation 7.5, we know that V is equals to U plus AT. So after calculating, you can get the value of u as 12 meter per second. From equation 7.6, we get S is equals to ut plus half at squared. That will give you 12 meter after calculating. Thus, the car will move 12 meter before it stops after the application of brakes. Can you now appreciate why drivers are cautioned to maintain some distance between vehicles while traveling on the road? Now we come on to the in-text questions that you can see in blue. Question number 1. A bus starting from rest move with a uniform acceleration of 0.1 meter per second square for 2 minutes. Find A, the speed acquired, and B, the distance traveled. Question number 2. A train is traveling at a speed of 90 km per hour. Brakes are applied so as to produce a uniform acceleration of minus zero point -5 meter per second square. Find how far the train will go before it is brought to rest. Question number 3. A trolley while going down on an inclined plane has an acceleration of 2 centimeter per second square. What will be its velocity 3 seconds after the start? Another few in-text questions on page number 83. Question number 4. A racing car has a uniform acceleration of 4 meter per second square. What distance will it cover in 10 seconds after start? Question number 5. A stone is thrown in a vertically upward direction with a velocity of 5 meter per second. If the acceleration of the stone during its motion is 10 meter per second square in the downward direction, what would be the height attained by the stone and how much time will it take to reach there? 7.6, uniform circular motion. When the velocity of an object changes, we say that the object is accelerating. The change in the velocity could be due to the change in its magnitude or the direction of the motion or both. Can you think of an example when an object does not change its magnitude of velocity but only its direction of motion? So figure 7.8 is showing you the motion of an athlete along closed tracks of different shapes. Let us consider an example of the motion of a body along the closed path. In figure 8.9a shows the path of an athlete along a rectangular track ABCD. Let us assume that the athlete runs at a uniform speed on the we are just on the right side of page number 83 of your NCRT. Straight parts A, B, B, C, C, D, and D of the track. In order to keep himself on track, he quickly changes his speed at the corners. How many times will the athlete have to change its direction of motion while he completes one round? It is clear that to move in a rectangular track once, he has to change his direction of motion 4 times. Now, suppose instead of a rectangular track, the athlete is running along a hexagonal shape path with A, B, C, D, E, F as shown in figure 7.8b. In this situation, the athlete will have to change his direction 6 times while he completes one round. What if the track was not a hexagon but a regular octagon with 8 equal sides as shown by A, B, C, D, E, F, G, H in figure 7.8c? It is observed that as the number of sides of the track increases, the athlete has to take turns more and more often. What would happen to the shape of the track as we go on increasing the number of sides indefinitely? If you do this, you will notice that the shape of the track approaches the shape of a circle and the length of each of the sides will decrease to a point if the athlete moves with a velocity of constant magnitude along the circular path. The only change in this velocity is due to the change in the direction of the motion. The motion of the athlete moving along the circular path is therefore an example of an accelerated motion. We thought that the circumference of a circle of radius r is given by 2 pi r. If the athletes takes t seconds to go once along the circular path of radius r, the speed v is given by v is equals to 2 pi r by t. When an object moves in a circular path with uniform speed, its motion is called uniform circular motion. So let's come to page number 84 of the motion chapter. Activity 7.11. Take a piece of thread and tie a small piece of stone at one of its ends. Move the stone to describe a circular path with constant speed by holding the thread at the other end as shown in figure 7.9. So figure 7.9, a stone describing a circular path with a velocity of constant magnitude. Now let the stone go by releasing the thread. Can you tell the direction in which the stone moves after it is released? By repeating the activity of for a few times and releasing the stone at different position of the circular path, check whether the direction in which the stone moves remains the same or not. Let's come on to the right side of page number 84. If you carefully note, on being released, the stone moves along a straight line tangential to the circular path. This is because once the stone is released, it continues to move along the direction it has been moving at that instant. This shows that the direction of motion changed at every point when the stone was moving along the circular path. When an athlete throws a hammer or a discus in a sports meet, he or she holds the hammer or the discus in his or her hand and gives it a circular motion by rotating his or her own body. Once released in the desired direction, the hammer or discus moves in the direction in which it was moving at the time. It was released just like the piece of the stone in the activity described above. There are many more familiar examples of objects moving under uniform circular motion, such as the motion of the moon and the earth, a satellite in a circular orbit around the earth, a cyclist on a circular track at constant speed, and so on. One viewer has constantly stayed since beginning. Thank you to that viewer. So here we come to the summary of the motion chapter, grade 9. Motion is a change of position. It can be described in terms of the distance moved or the displacement. The motion of an object could be uniform or non-uniform depending on whether its velocity is constant or changing. The speed of an object is the distance covered per unit time, and the velocity is the displacement per unit time. The acceleration of an object is the change in velocity per unit time. Uniform and non-uniform motions of objects can be shown through graphs. The motion of an object moving at uniform acceleration can be described with the help of the following equations, namely v is equals to u plus at, s is equals to ut plus half at square, 2as is equals to v square minus u square, where u is the initial velocity of the object which moves with uniform acceleration a for time t, v is its final velocity, and s is the distance it traveled in time t. If an object moves in a circular path with uniform speed, its motion is called as uniform circular motion. With this, we have completely done the reading of chapter 7 motion. In case anybody has joined in between, wherever you get free time or in need, just come to my channel and you can play this live. Don't forget to hit the like button, or in case you want to comment, you can comment. I will be clearing your doubts. Stay connected. We'll be back with another video. Thank you.